Hello, I'm XenoCow, and today I'd like to give a full and detailed breakdown of that camera that I made and showed a couple weeks ago. If you are not interested in programming or system design stuff, maybe this isn't quite the video for you, but if you are, then stick around. I think you might learn some interesting things about interesting ways of using YOLOL, the Starbase's in-game programming language, and maybe just how to design such a large system. So, without further ado, let's get into the system itself. So first, let's take a very overall kind of view of how it all works. We have the Rangefinder Array, that's 625 rangefinders packed very densely. And those can tell, each rangefinder can tell a depth. It shoots out a laser and shows you how far away the thing is at the end of that laser. Then that feeds into a large array of YOLOL chips, and we'll talk about that. That's the primary thing we're going to be talking about today. And then we have a viewfinder, so we can see in real time what it is the camera is looking at, and a display for showing the progress, what's actually happening at the moment, starting and stopping, or at least starting, I don't have a stop button, the camera taking process, and of course showing the final output image. Now let's talk a bit more about what it is those YOLOL chips are actually doing and what how the system goes about taking a picture. So the very first thing, we have our Rangefinder Array, and it'll feed into some chips that display for the viewfinder. And then let's talk about taking a picture. So to take a picture, you press the start button, and then after that, you're going to set the focus. And the focus, what I mean by that, as this isn't an optical camera like one you take pictures with normally. What I mean by focus is finding the farthest and closest point of the subject that you're looking at. So let's say we're looking at that asteroid I showed in the demonstration video. The farthest point that we see on that asteroid and the closest point that we see, that's what we save as a min range and max range. Next thing we're going to do is we're going to calculate range levels. And so since we can only show so many different shades of filled in pixels on our display, we need to chop up our range so that we know how far each different shade of filled in pixel, where that sits. And we'll talk it'll make more sense a little bit later. Next thing we need to do is we need to encode the pixels, and so all of these first three chunks, they all read straight from the Rangefinder Array, and so you need to keep the image still during that time. But the encoding process, what that does is it looks through every single rangefinder and figures out which level that pixel should sit in, and that is saved as numbers. Just like from 1 to 9. It doesn't use 0 because if you were to have a number that starts with 0, that 0 gets chopped off. So we only get that many levels that we can use. So then after we've encoded all of our pixels into numbers, we don't need to look at the rangefinder anymore because we have the whole image saved. And we can decode it into the actual color values or filled values. It's kind of black and white image, right? And that looks through all of these chunks of the encoded image and converts those into the string, the characters that are displayed on the display. And then the printing step puts that all on display, and then after you press the start button again, you can clear the screen. So that's the entire process. Let's start with the simplest things first, and then we'll just go from the beginning to the end of how an image is taken. So the very first thing is we need to just understand what the rangefinder is. So we have all these rangefinders, and they are, we have 1 to 25 on the top row, and then 601 to 625 at the bottom, and then I have all the in-betweens, and they're all labeled AA, AB, AC, whatever, all the way through YY. And the viewfinder, the pixel, they're warning light buttons, I think that's what they're called. They are labeled in the same way, but they are mirrored so that it's because you're looking from the back of the rangefinder, you need to have the order of things the opposite, and they have a B in their name as well, so that they can all be differentiated within the code. And to actually display to the viewfinder, it's a very simple piece of program, but because I want it to be real time, there are lots of them. I think the majority of the chips, you can see here, all of these are all for the viewfinder only. But each chip, all it does is it just looks at, what is this, 1, 2, 3, 4, 5 different viewfinders, and if there is something in the way, and so this :M, that is the maximum range that the viewfinder is looking at. So the very maximum possible is 1,000 meters, but you often want it to be less than that. And so as long as there is something that is less than that, that means there's something that the viewfinder is looking at. And so we just light up that pixel, that warning light. So that's all that all these chips do. And since it's just a single line, it can run in just a fifth of a second, so it's mostly real time. But because we don't want it to take 2/5 of a second, we have one chip for every 5 pixels. Next, let's talk about the main controller. So this is back to the part of the program that actually takes a picture. And we'll break down this code piece by piece, and we'll do the same with all the other programs. So this is just a single chip, and the very first thing it does is it just holds on to a bunch of status messages that can be displayed so that while you're taking the picture, you know what step of the program it's on. So we save all these strings. Strings are just, if you're unfamiliar with programming, it's just text, words, letters. And then it waits for the start button to be pressed. And so while it's waiting, it'll just keep going back to that line 4 until the start button is pressed. Once it's pressed, it turns off the start button. All the start signals from now on, they'll turn off their start signal once it sees it, so that it doesn't accidentally restart once it finishes whatever it's doing. It's a good little tip if you need some sort of start thing. Just like here we see :start, then start equals 0. So that means when it sees start, it'll do whatever's in that then section, but it won't repeat again until whatever the outside thing that turns on start will start it again. So then it goes through actually taking a picture, just running each section, focus, range, encode, decode in sequence, and then it again waits for the start signal so that it doesn't clear the image automatically. And then once you press the start button again, it'll clear the screen and go back to the very beginning. So it's a pretty simple one. Moving on, let's get to focusing. So focusing is a little bit more complicated, and it has both a controller and then a series of chips that do the actual finding of the focus. And if you start, focus S. For most of the variables, I think I named them consistently, where there'll be the section, the process name, and then S for start and D for done. And so if start, we're going to start the first focus layer. So the focusing needs to happen in 2 layers. We'll get to a little bit more of that in a bit, but the next thing it'll do is going to sum up all of the done signals. And so what that means is that, so this A, B, C equals all these variables, this is checking to see if every single one of the first layer of focusing is done. And again, we'll get to what the actual focusing process is in a moment. So we want to see, are they all done? And then this next line here, line 5, we add up all of the sub-sums, I don't know if there's a proper name for that, the subtotals, and check to see if they are, if it all adds up to the final number that we want. And if so, then we're going to start the next layer. And this next layer, because we had all these separate focusing chips, we need to then check them all against each other one last time, or pretty much one last time. And so we do that with just only 2 now, because we've started with lots of small focusing chips, And then they all add together and find their results, and then we can check those sub-results, and then second layer, and then once those two are done, we just add them together and check to see that they equal 2, greater than 1. Then we're going to go to the next line where we check, we get one more time, we compare, now we have these two layer 2 results, and we get our final min and max, and so we just check to see which one it has the actual minimum and which one has the actual maximum. And then we go back to the beginning. So now what does the actual focus chip do? So again, it has a start signal, same thing, just like normal, check to see if it start. We have this O here, this is an offset, so if you remember back on the Rangefinder Array, they are not all right next to each other, so some of the rangefinders are slightly behind other ones, and so we have this offset, this O. We'll see this again, but just to keep track of how far from the front that particular rangefinder is. And so when I made all of these focusing programs, I had to keep track of which particular rangefinders were on which level. And it happens to be, you can follow along, there's like even, odd, or even odd, odd, and odd even. They're not exactly even and odd, but letters, like A, what I considered odd, I think, and then B would be even, and so on and so forth. And so that's how it's stacked up at the end of the day. But in any case, this one has a offset of 72 centimeters. So and all these lines that you're going to see here, they're all the same, so we just set our max to 0 and our min to the view range. So that's just setting our maximum to the smallest possible number and our minimum to the largest possible number, so that anything between those will properly set our mins and maxes. And we're going to, just for fitting everything into one line, we're going to get this temporary variable r and set that to the rangefinder's range, the :AA, for example, in this first line, with the offset. And then we're going to have these two sections here. The first one is going to set the max if our offsetted range is larger than our total maximum that we have, which at the very beginning is 0, and that there's actually something there, right? So this next part, if :AA is less than :M, again, remember :M is the view range, so it has to still see something there. And then we do the same thing pretty much for the minimum. We just see if there's anything there again, and if it's smaller than our current best minimum. And then we save that minimum and maximum each respectively if they are actually that. And we just do this for a whole bunch of chips, a whole bunch of rangefinders. And then at the very end, we save in a memory chip so that other parts of the program can access it, are M1 and N1, and we say that we're done. And we go back to the beginning. And we do this for every single rangefinder. And so this is the layer 1. Layer 2 looks exactly the same as this, except that instead of looking at the rangefinders, it'll look at these M1s and N1s, so that we can look at the results of all of the chips, or all the layer 1 chips. Next, so now that we know how far the front and back of the thing that we're looking at is. Now we need to split that up, and this is just a pretty simple little chip. It's just one. We have our start. We just check to see if it's time to start doing this, and then we figure out what 1/8 of that total distance from the front to the back of our subject is, and then we're going to just go through every single level and just start from the minimum, and we're going to add 1/8, and we're going to add 2/8, 3/8, 4/8, all the way through 7/8, and then the very last one, I call it level 1, it's a bit confusing, but in any case, level 1 will be the maximum range. And then we say we're done. We go back to the beginning. Next thing we're going to do is we're going to now encode all of the ranges into the various range levels. Instead of just being 400 30.5 meters, it'll be 2. Not in meters, but just range level 2, and so that's what color it'll need to be later. This one's actually a very simple one. All we do is we just, if start, we start all the encoders, and this one can happen in parallel, so they all happen at once. And then, just like before with the focus level 1, we just add up all of the done signals of all of the encoders. Because you'd think, well, why do I need to do this if I know how long it's going to take them? But some of them are not the same length as others, so they don't all finish at the same time. And just, you may not, although YOLOL is supposed to run all at once, sometimes there's slight offsets in how actually long things take, and so sometimes it's better to double check that everything actually, if you have lots of things happening at once, that they all finish before you start the next task, whatever that may be. So then we just see if we're done, then we go back to the beginning. That's it. The controller is very simple for this one. The encoder is actually not too bad either. So the first thing we're going to do is we do this in 2 lines, but again, we have our start signal, and if it's time to start, then, we do a little bit of this at the beginning, but we're going to save variables for 10 through 10, or 1 with 12 zeros, so that we can then later use these for constructing our encoded image. But just remember that we have all these 1 or 10 through 10 to the 12th power variables later. I labeled them Q through Z, and then Z1 and Z2. And we also hold on to our offsets because we'll need those for some of the pixels. And then all of these lines are going to be the same thing. It's a little hard to tell what's going on, but it's actually not too complicated. So first we get our rangefinder with the offset so that we don't have to subtract that offset every single time we want to check the range, and so that just saves a ton of space and gets us to perfectly fit this all in one line. And then for all this, you can see at the very first one it says A equals 1 plus RF less than colon R1 plus RF less than colon R2. And so all we're doing here is for every level that our range is less than, we're going to add 1. So if the checking something is less than, equal than, greater than, whatever it is, right, those kind of logical operations, they result in a 1 or 0. So you know that if let's say the first one, it is less than range 1, we know that will, if it is, it'll just be 1. And so it'll be 1 plus 1. Then we go to the next one. Is it less than range 2? Also, okay, yes it is, then add another 1. And so we do this for every single range level. And we start with 1 again, because if we have 0, then if 0 is at the very beginning of this chunk of the encoded image, then it'll disappear because there's no such thing as a number that starts with 0. Right? It would just be the next digit. Anyway, so we do this for a whole bunch of rangefinders, and so we get each one of these now encoded as a single number. But we need to put these all together so that we can easily move this around. Otherwise, we'll just have lots of numbers. And so to do that, we stick them all together using those various powers of 10 before. And so at the very bottom here, we have pick 1 equals m times z2. And so what that means is it'll put whatever the result of the m rangefinder, the very last one, it puts that at the very beginning of this encoded chip, or this encoded chunk of the image. And so we just do that for all of our rangefinder results, our encoded ones, with all the various places in this image, in this number. And that's what all this multiplication does. It moves that number to that the digit that we want in the series. So now we have all of our image encoded into 1 through 9, and in these chunks, these large numbers, they look to the YOLOL just like a number, but we're holding on to information with each digit. Now here's the precursor to the most complicated part of this entire program. So decoding into the pixels is very complicated. However, it has actually one of the most simple controllers. So we just, again, as always, check to see if it's time to start. Again, the main controller is what's controlling that, sending those start signals, and keeping track of the done signals. And then we're just going to run the first decoder, and then run all the other ones in series. And with the decoding, unlike encoding, which could happen in parallel, because for the way that you print to the screen has to happen in order. You can't, I guess you could start in one place and then move around, but it'd be more, anyway, this is the way I did it. So you have to print, you stick a bunch of characters on it, and then the cursor will move to the next spot on the display, and then you stick a bunch more characters, and so on and so forth, all the way until you get to the end. And because of that, the way that we store the pixel characters is sequential, and this can't happen in parallel. So a lot of the program can happen in parallel, and so it's very fast. This part is very slow. And we'll get to that in just a moment. So let's talk about this beast of a program. This probably took me the most work out of anything, because there's a lot going on here. Very first line is very simple, though. All we do is we just remember what empty looks like in both this E, that's for empty, and then N for nothing, I think. But the E, that's a string of just empty spaces, so that's if there's nothing there. And N, all ones, that means that there's nothing there in the encoded version. And we use this later on to, if there's a big chunk of the image that's empty, we can just skip the whole thing and just say this is all empty, and so we don't have to do so much work there, and saves a little bit of time. Next, we're going to go to this next line, and here we just check our usual start signal, and if start, we then move on to the next line, just like normal. And here we've got a few things going on here. The first thing we're going to do is we're going to check if this is the first loop. So there's going to be some looping in this one because it has to go through lots and lots of parts of the image. I call them chunks, I guess. And so if it's the first one, then we're going to start by looking at the first chunk, and we're going to assign that chunk to P. So an internal value called P for picture. And then we're going to set our L, that's the loop number, to 1. If it's true. Otherwise, we just move on to the next part. And so then we have this other if statement to check to see if there are any pixels in P, because we're going to be slowly chopping off the encoded digits as we go. And we'll get to that in a little bit. But if there is still something, then we're going to set R for remainder to P mod 10. That means we get rid of everything off of P except for the very last digit, so whatever's in the ones place. So imagine you divide the image by 10, whatever the remainder is whatever's in the ones place. So now we have just the very last digit, and so we can look at that particular pixel. And then let's say that there are no, actually we're going to start with the if there is something there. So we'll follow this path. So if there's something there, we're going to, again, get this next pixel. If there wasn't, then we would move on. So let's say we got the next pixel and there was something there. Then what we're going to do is we're going to, I already mentioned it before, but this, with the empty optimization, I guess you could call it, we're going to see is P, so that's not the particular pixel, but an entire row, or entire chunk, if all of that is empty. And if it is, then we are going to set all the pixels, so this P stir 1, 1, that means the picture string 1. So that's the first part of first chunk, level 1, or layer 1, and then layer 2, layer 3, because the display has 3 different layers, and so we just want them all to be empty, completely empty. And we set that all to empty, and we also set P to empty so that later on it'll make more sense, but we need to make sure that we tell the program there is now nothing left to decode of this particular chunk of the image. And then from there we go through to removing, we go to the next line, and we still have to do this, even though it would be better not to, but just for the sake of the program working, it's hard to skip over some parts, and so you have to sometimes do things unnecessarily. But what we're going to do is this first kind of strange thing here is it's just removing the last digit. So imagine that we didn't. There's a lot. Let me see if I can. I'll back up a bit actually. Let's say that there was a pixel, or it was there was not empty. There was something there, right? So it didn't equal nothing. We're going to go to 9 plus r, and so that r again is the remainder. That's the particular encoded pixel that we want to look at, and line 9 plus r means that we go to either 10 or all the way through 18, depending on what that encoded digit was. And so all of these down here, these are just setting the various string levels to this level 2-1, 3-1, 4-1, etc. are just the particular characters. So a B or a colon or a apostrophe or whatever it is, right, that we want to actually put on the screen. And so we just add that character to the respective strings, and then we go back to 5. So that's what happens if there's something there that we need to decode. And then it bounces back to 5. All right, let's get to 5. So now at line 5, this first part, it first subtracts off the digit, the last one. So whatever P is, it's going to end in a 0. And now we want to divide it by 10. That's what I'd want to do. However, it turns out that when you're working with numbers this large in YOLOL, for some reason if you were to divide it, just say, I want just to divide it by 10, chop off the last 0, that doesn't work when you have numbers this large. For some reason, you get strange decimal points. I think there's just some floating point errors or something. But if you do it this way, where it's very strange. So instead of dividing it by 10, we actually subtract off 9/10 of the entire value, and that's the same as dividing by 10. Again, it's very odd, but if you happen to run into this problem, then this is a way you can kind of get around that strange floating point error, where you just think of another math operation that might keep numbers smaller through the process. In any case, all that does is it just chops off the last number. And then the next part of this line is we check to see if we're done. So we want to see if we have this D that holds on to whether we finished up looking at all of the chunks, and that times if our P less than 1, that means that if there's absolutely nothing left, it's 0. Right, we've subtracted off everything there is from this particular chunk. Then we're going to, so that's setting the done signal, right? And then this go to actually is the if. It's not a normal if statement, it's a go to, but we're doing some math for which line it actually goes to. And so we're just we'll go to line 2, the very beginning, that very beginning start, if we are both done and there's nothing left in the particular picture chunk. So that's what this if done does. And let's talk about the very last part we haven't talked about yet, which is, imagine again we've finished one loop, so we've gone through every single pixel in this particular chunk, and they've all been chopped off, but we're not done yet. So we go back to line 3, and Now, this second if statement, we see, oh, actually, there aren't any pixels left. So now we're going to go to line 6. And what line 6 does, this is just we're just checking our loop number against lots of different loop numbers. And for each respective loop, we're going to change P, we're going to assign to P the next chunk of the image. And so we just have all these various, these pick 4, 5, 6, whatever. They are all the encoded chunks of the image, and once we get to that part, we're going to start working with that one. So we set P to that chunk. And then after the very last one, we set D to 1 so that we remember once we're done with that loop, that we should finish up and go to the beginning and set our done signal and whatnot so that the controller can start the next part. I hope that makes some sense. I think that this diagram here, this little flowchart, is much easier to look at than the actual code. The code, it's a bit dense, as YOLOL always is, but anyway, this was quite a bit of work, and I hope you can learn something from this one. From now on, it's much simpler. The next part is we need to actually put it on the screen. That's pretty simple. We just, again, check to see if it's time to do that. And then we're going to set the input of the display, the grid display, to all of the strings added together for layer 1 first. Then we do layer 2 and then layer 3. So then it just stacks them all on top of each other. That's printing. Very simple, at least compared to the other stuff. Then we go to clearing. So if you remember, if we press the start button again, then we're going to clear the image. And all we do is we just do a couple things in parallel here. First we clear layer 1, we clear layer 2, and clear layer 3, and at the same time we also empty out all the strings so that they're ready to be filled again next time we want to take a picture. So that is the entire program all at once. It's a beast, but and I'm sure there are plenty of places that all of you will have optimizations that could make things faster. I know I only really have that one thing to speed it up because the decoding takes the most time. If it's an empty image, it'll take not very long. If it's a completely filled image, it'll take, I forgot what it was like 12 minutes or something. So that's how I made this. And one thing, I guess, to add to all of this is that for a lot of these programs, there were so many chips. And so if I tried to remember all of the particular variable names and write them in by hand, it would have taken forever. And so what I did for a lot of them is I wrote Python programs. And that's why you can actually, one of the reasons you can see the YOLOL code here is highlighted. It has the syntax highlighting so that you can understand what's going on. But I wrote Python programs to print to a text file all the chip programs. There's a lot of, I'm saying program a lot. But I made a program to write programs, especially for things like when there's all the offsets to deal with. I wasn't going to be able to remember that. But what I could do is I could have the Python program remember, okay, for these rangefinders, we need to have this offset, or these other ones, we need to have this other offset, and just generate a bunch. And another nice thing about that is, let's say, and I had to do this a few times, you make a ton of the programs and it doesn't work. Now, if you were to have done it all by hand, now you have to go through every single chip by hand and change the things and make sure that you didn't forget anything. But by writing the Python program to write the YOLOL programs, I just change the one Python program. It spits out a ton of the YOLOL programs, and then I can just copy and paste those in the SSC, and you are good to go. I mean, copying and pasting does take a little bit of time, but it takes far less time than doing it manually. So that's another thing. If you have a project that is many, many chips, and I've got over 200 chips in this one, I highly recommend learning some Python before you start that kind of thing, or maybe you can do it at the same time. But it saved me probably days of time. I don't think I would have been able to do it otherwise. Anything else? I guess I'll end the video by showing a little bit of some footage here where recently at the EOSCon, some people let me take pictures of their ships. There's one person, he had a pirate ship, and so I took a picture of his, and he stuck it inside his ship. Unfortunately, the field of view of this camera is pretty limited, so for large ships, it can only take a chunk of it. And then another person has a ship that looks like a sports car, and so I took a picture of that too. So here's that, and it was fun to just take the camera out for a spin and actually, get to share these pictures with people, like a giant, very, very slow Polaroid. Alrighty, I think that's plenty enough. If you have any questions about this, or YOLOL programming, or have suggestions for how to make it better, I think I'm probably done with it. I don't know if I'll go back and change anything, but if you do, feel free to tell me about that. This was XenoCow, signing off. Oh, and, of course, as always, dislike the video and unsubscribe.